Welcome back. It's nice to be back in the classroom, and welcome back to the folks at home. Um, Announcements, we do have our next test is on Friday, so that's worth starting to think about. As I've said before, ordinarily I don't care if you come to class or tune in by Zoom, but if you are able to, I want you to be in class on Friday. I know some people are in quarantine now, and so if you're not going to be here on Friday, let me know. Otherwise, I will plan on seeing you then. So what we're going to do for this week, today we're going to do new stuff, which will not be on the test. Tomorrow, we're just going to do review things. I'm going to prepare a little review sheet like I did last time, and we can talk about any questions that you have about anything. I can say at this point, just sort of vaguely, what's on the test is everything from homework number, I believe it's 6 through 10. 10 is the one that's due tomorrow. I'm just going to look that up and make sure. It starts with the oldest material that will be on the test is about the hyperbolic trig functions, which is kind of a long time ago. I'm just looking at sorry, I should have written this down before. It is number 5, sorry, not 6. So this goes from hyperbolic trig functions all the way through to the present day. Maybe I will just shout out for now what the topics. There's kind of a lot of topics. So we have the hyperbolic functions, then L'Hopital's rule, then integration methods, which was parts, trigonometric integrals, trigonometric substitutions, and the partial fractions. And then we did improper integrals, and then we did the sequences and series stuff. So there's kind of a lot. I will, like I said, tomorrow we'll talk in a lot more detail about the test. Does anybody have any questions at this point?
You put some specific extra review on the trigonomic integrals on the review sheet because I know that I'm very rusty on this.
Sure.
Anybody else, but we're going to touch those for a while.
Yeah, right. A lot of these things, since we've been talking about sequences and series, you will find that stuff a little rusty. So yeah, we'll be sure to do a bunch of examples of those.
Is there any way you can email us out like a list of topics to do today so that if we're going to start studying, we have that list and we can work through the book with that list?
Sure. I mean, you can look back over the homework assignments, and each, the list of sections is there. But
6 through 10?
yeah, 5 through 10, the homework assignments. Yeah, I have been, uncharacteristically for me, I've been working on the review sheet already and almost done with it. So I'll send it out as soon as I'm done with it, sometime this afternoon probably. All right. It's because my kids have spring break this week, which means trying to do stuff ahead of time because they're going to be around more often than usual. All right. So homework is due tomorrow. It's stuff about the comparison test, which is what we've been doing lately. All right, let's get down to it then. So at the end last time, we were doing some things that you guys were working through, and I failed to judge the time. I didn't leave enough time to go over those problems. So I want to do that just to get us started. Sorry. All right. I wanted to go over the second of those. Most people did the first one fine. The second one, I also have a confession to make. There was a typo in this problem, which made it too hard to do. Let's all just do this together, just as a little refresher. N plus 2 to the n over 5 to the n plus n. When I wrote this last time, that I had as multiplication, n times 2 to the n, which really makes it quite a bit more difficult. I don't know how many people actually worked through the whole thing. Actually, probably you didn't work through the whole thing, because with multiplication up there, the methods that we've talked about are not really sufficient to do it. Let's do it anyway. So we are going to use what we call the limit comparison test. This was the trick we were using last time, in which you look at this and you sort of look at what we call the dominant terms. You say that thing basically looks like, you look at the numerator and the denominator, and you think when the n is really big, what's the part that really matters? And the answer is, on the top, what really matters is the 2 to the n part, because when n is very large, adding n really doesn't do anything to that. Now, if we're multiplying by n, that actually does make it much, much bigger. But 2 to the power n, adding n onto that really doesn't change its value very much. And then on the bottom, same idea, 5 to the power n is the more important thing on the bottom. All right? So that's what we're going to divide by. Remember, you call this like an, and you call this bn, and you do the limit as n goes to infinity of an over bn. And if this, the comparison test, the limit comparison test says that if this limit exists and is not 0, then the convergence of the series of ANs is the same as the convergence of the series of BNs. That is to say, either they both converge or they both diverge. Anyway, what is this? You usually, this amounts to some kind of giant fraction inside a fraction, but it's going to be n plus 2 to the n over 5 to the n plus n, divided by 2 to the n over 5 to the n. So that's the same as multiplying by 5 to the n over 2 to the n. So I got, and it goes to infinity, n plus 2 to the n over 5 to the n plus n times 5 to the n over 2 to the n, right? Instead of dividing by the fraction, we multiply by the reciprocal. And then we can multiply that thing in, distribute, if you will, 5 to the n times n. So this is lim, n goes to infinity. This is n times 5 to the n plus 2 to the n times 5 to the n would be 10 to the n. Yeah, that's right. I confused myself. And then on the bottom, I get 10 to the n plus 2 times, n times 2 to the n. All right. My intention is to take the limit as n goes to infinity here. What we do in order to do that in a fraction like this is typically you divide out by the biggest power of n or the biggest something or other. In this case, the biggest thing on the top is actually going to be 10 to the n. So I'm going to divide everything through by 10 to the power n. And we get, n 5 to the n over 10 to the n plus 1 over, I should have written lim again. Come on now. I didn't do the limit yet. And then on the bottom, 1 plus n times 2 to the n over 10 to the n, right? And then those parts with the 10 to the n's in the denominators will go to 0 because the 10 to the n, 10 to the n is much, much bigger than n times 5 to the n. So these guys become zeros, and I end up with 1. And what does that mean? It means that the two series have the same convergence properties. Either they both converge or they both diverge. So sum n plus 2 to the n over 5 to the n plus n and sum 2 to the n over 5 to the n have the same convergence. And what is the convergence of 2 to the n over 5 to the n? Well, that one you can write as 2/5 to the n, right? And this is a geometric series. Two-fifths to the n is a geometric series. Each term is just 2/5 times the previous term, right? So this is geometric, and the r is 2/5. Each next one is 2/5 times the previous one. Anybody remember the rule about this? Does this one converge or not? It does converge. The rule for geometrics is if the absolute value of r is less than 1, then it converges. And this really is less than 1. So the absolute value of r is less than 1, so it converges. All right, so that means the 2 to the n over 5 to the n converges, so that means the other one converges, which is what we really wanted to know all along. So the sum n plus 2 to the n over 5 to the n plus n converges. All right, a little tricky, I would say. Any questions? questions about that one? This is how we do them. Sorry I didn't finish this one up at the end last time. Didn't leave enough time. One thing, just in the spirit of reviewing for the test. Do you really believe me when I said that? I said that those two guys, remember these parts, here and here, they became 0. Do you really believe me? That I said n times 2 to the n over 10 to the n. This limit is 0.
Yeah, because the one on the top is growing exponentially larger than the one on the top. So there will always be a fraction approaching 0 as the numbers get larger.
Yes, it's true.
So it makes like fractional sense.
Fractional sense. You mean like a little bit of sense?
Yeah.
Yeah, I mean, so what I said was the bottom is getting much bigger than the top is. I mean, that's true, although that's a bit of an informal way of saying this. Really, the true way to evaluate this limit is by doing L'Hopital's rule. Because what we have here is a fraction in which both the top and the bottom are becoming infinite, right? The fact is, I said the bottom one is becoming infinite sort of faster than the top one. But the real way to handle that situation is by doing L'Hopital's rule. So how I would do this one, this is slightly tricky, but I thought I might as well mention it just because, you know, you do the derivative on the top and on the bottom. Although in this case, the derivative on the top is kind of a pain because you have to do the product rule. Usually when you do L'Hopital's rule, the idea is you do the derivatives to make the top and the bottom simpler than they used to be. But if you do it directly here, the top will actually get more complicated because you have to do the product rule. So I'm going to do a little trick, and that is, let's move the 2 to the n into the denominator. So I'm going to rewrite this as just n on top. And then I'm going to write it as 10 to the n over 2 to the n in the bottom. Ordinarily, you wouldn't really want to do this, but in this case, I mean, it certainly works. And can you simplify 10 to the n over 2 to the n at all? 5 to the n, yeah, that's right. So now we have lim n goes to infinity, n over 5 to the n. And now I hope you still believe me that the bottom is going to be very, very, very big, whereas the top is going to be, you know, pretty big, right? The bottom definitely is getting bigger faster than the top. But the real way to demonstrate that is by doing L'Hopital's rule. So I do the L'Hopital's rule here. This is my L'Hopital step. On the top, I get 1. And on the bottom, the derivative of 5 to the n. There's a rule for that. Does anyone remember this rule? There was a rule about derivative of b to the x. It is not x times b to the x minus 1. That's the... Something like that. Yeah, it is b to the x times the natural log of b. Or ln b times b to the x. So in this example, I get 1 over 5 to the n times natural log of 5. And now we can do the limit. The top is simply 1, and the bottom is going to be infinite. All right, so this now becomes like 1 over infinity, right? So the limit equals 0. So this is in full detail how you would do those limits in that problem. All right.
Do you expect us to have all that work here now?
I don't think so. I mean, if I just gave you this like as its own problem, then I would expect you to be able to do that with using L'Hopital's rule. But if the larger problem was this one over here, I think I would take your word for it that this becomes 0. All right. Excellent. I think I'm ready to go on to the next section. So this is the end of the stuff that will be on the test. That limit comparison test, you should expect to use it on the test. I mean, there's kind of a lot of material, so probably not everything's going to make it into the test. But when I say this or that is going to be on the test, really what I mean is it might be on the test. All right. Okay, the next section in our book is called Alternating Series. Alternating series. This is another kind of convergence test, you know, in the same theme as what we've done so far. We've talked about the integral test and the comparison test. Those tests don't always apply, right? Remember, the integral test is only used when a function or when the series terms are decreasing, and the comparison test is only used when the terms are always positive. So none of these tests work in all cases, which is why we need to talk about so many different tests. Here's another one. It's called the alternating series test. Let's talk about alternating means that the signs alternate. You know, they go plus, minus, plus, minus, plus, minus. So alternating means that the signs of the terms alternate. That is, they go positive, then negative, then positive, then negative. So an example of an alternating series, like this is everybody's favorite alternating series. This goes minus 1 plus 1, minus 1 plus 1, minus 1 plus, etc. Right? And this one we've talked about before. This one diverges. That was one of the early examples that we did. Because the partial sums, as you go along, remember how you tell if it converges or diverges? Just using definitions, you look at the partial sums. The sum of the first one thing is -1. The sum of the first two things is 0. The sum of the first three things is, again, -1. The partial sums, they just become -1 and then 0, then -1 and then 0. And that doesn't converge to anything. So anyway, this one diverges. How about, here's a more interesting one. -1 to the n over n. This one looks like -1 plus a half minus a third plus a fourth minus a fifth, etc. Does that one converge or diverge? Actually, this we have not discussed, this particular example here. It turns out, just because I know stuff, this one actually does converge, although it's not obvious that it does. But this one does converge, and in fact, it converges to this number, the natural log of 2. This is strange, very strange thing. But if you add up all the fractions in that way, alternating the signs, this one gives you negative ln2, just because we started with the minus sign. If you alternate the signs the other way, plus, minus, you get positive, the natural log of 2. Very strange, in my opinion. Or you can do some variation, would be something like, in our book, they like to write their alternating series with instead of n exponent, with the n-1 exponent. The effect of that is it makes it so that the first term is a plus rather than a minus. When you use the exponent of n, since n starts at 1, you always begin with the minus sign. But if you use n-1 like this, then you begin with a plus sign. So this one looks like 1 minus a half plus a third minus a fourth plus, etc. And this one, if you actually compute the series, it adds up to plus natural log of 2. Although we're not going to get into the details. That's a kind of a difficult computation. We're going to talk about it much later, actually, but not now. All right. All of these are examples of these are alternating series. The signs bounce back and forth. That's all it means. All right. Alternating series. If you can visualize this, I suppose, by if you want to like plot the terms of an alternating series, what they look like is, maybe the first one is positive or maybe it's negative, but beyond that point, they just go back and forth. The next one is negative, the next one is positive, the next one is negative, the next one is positive, right? The alternating series always looks like that. I tried to draw these dots with no pattern to them, except for the fact that the sign of each one is the opposite of the next one in the previous one. It goes back and forth every time. So down and then up and then down and then up and then down and then up, right? This is an alternating series. All right, and there is no guarantee that an alternating series will converge. Like in this example, this very first one, this one diverges. It is alternating, but it diverges. This one is alternating, but it converges. So the alternating series, some of them converge, and some of them diverge. And what the alternating series test is about is sort of about which ones will converge. And here's the basic idea is that these will converge when the terms themselves go to 0. And what I mean by that is, you know, if it bounces back and forth like I did before, but every time the dots are getting closer to 0. Like that, right? This is an example where the signs, they go back and forth every time, but each time they go back and forth, but they get closer to 0 as you go down the line there, all right? In this case, such a series that comes from adding those things together, it actually is guaranteed to converge, all right? So the series will converge. It doesn't converge to 0. I'll just say maybe not to 0. Because now, like, if you just look at the dots, it looks like the dots are converging to 0 as you go out to the right, and they really are. But remember, the series is not where the individual dots go. The series means when you add them all together, where does that go? And that can go somewhere else. You know, could be more than 0, could be less than 0. But the idea is when the terms, individual terms, go to 0, then the series will converge. So I'm going to write that as a theorem, and this is what our book calls the alternating series test. And this is what you use. If you see an alternating series, this is how you can demonstrate that it converges. If I'm going to say in this alternating series, if your alternating series looks like B1 minus B2 plus B3 minus B4 plus etc., you could write it as a series like this, -1 to the n minus 1 times Bn. So if you have an alternating series, it goes back and forth with pluses and minuses, and the things that you're adding and subtracting are some sequence called Bn. In this alternating series, if two things have to be true. The first is that the b's are decreasing, and the next is that lim n goes to infinity bn equals 0. So here it says bn plus 1 less than or equal to bn. That means the next one is always smaller than the previous one, so the b's are decreasing. But not only are they decreasing, but they actually are decreasing in such a way that the limit goes to 0. All right? If that's true, both of these things are true, then the series converges. -1 to the n minus 1 bn converges. Converges. I put two n's there. Converges. All right? So the two things have to be true. The individual terms get smaller every time, and also their values are going to 0. If those two things are true, then the series converges. All right? I'm going to try and give us some idea of why this is true. In this class, we don't do a lot of proofs of the theorems, although this one you can actually show pretty nicely, sort of on a picture, why you should believe that this is true. So I want to talk about the idea of the proof, sort of a picture of this proof. Remember, we are adding together these b's, adding and then subtracting, and then adding and then subtracting. So what I want to show is that it converges. Of course, when you look at something converges, is all about the sequence of the partial sums. So the first partial sum is just b1, that's just the first term. The second partial sum is the first two, so that would be b1 minus b2. The next partial sum is b1 minus b2 plus b3, right? These are the partial sums. And I want to try to explain why, if you keep on doing this in this way, these s values, the partial sums, will eventually stabilize to a particular number. All right, they don't like become infinite or negative and infinite or anything like that. They will stabilize to a particular number. Check it out. You can kind of exhibit these numbers on a little picture. So I'm going to draw a picture of the number line, maybe over here. And I don't know what any of these numbers are, but S1 is equal to B1. Let's say 0 is here and B1 is positive. B1, which is the same as S1, all right? B1 is the same as S1. Get this little thing out of here. There we go. All right. Where on the picture is B2? Sorry, S2 is what I want. Where on the picture is S2? S2 is equal to B1 minus B2. So you could think of this as if you start here at B1. Come on now. Start here at B1 and then subtract B2. That means you go to the left a bit. Am I going to go all the way past 0 or not quite past 0? The answer is not quite past 0 because I'll end up maybe there. I'll say this is S2. And this distance right here is B2, right? Because S2 is supposed to be B1 minus B2. And why did I not overshoot 0? It's because B2 is less than B1. Because that's part of what we are assuming for this, this theorem here. The b's are decreasing, right? Each next b is smaller than the previous one, which means when I subtract b2 here, this distance here is less than b1, which is the whole distance from 0 over to b1. Since b2 is smaller than b1, when you subtract it, it does not go past the 0. It actually goes at someplace in between, all right? Then to get S3, the next thing I'm going to do is add b3. So that means from here, I move to the right a bit by the distance of whatever the number b3 is, and that's what S3 is. So this right here is S3. And B3 is smaller than B2. That's why this little trip to the right that I took right here is only a little bit. It doesn't like stretch all the way over to here because B3 is smaller than B2. All right? To get to the next S4, I'm going to move to the left a little bit, but it will be quite a little bit. Remember, every little bit we add in each step is smaller than the bit from before, and they always go in opposite directions. So the next one that I add on will go to the left just a little bit, B4, and I'll end up here. Here is S4. All right? Where does it end up when I go to the next one? Well, I hope that you can see sort of what's going to happen here is, you know, the next one will go over to the right a little bit, then to the left a little bit, then to the right a very little bit. Eventually, these little bits will sort of stabilize at a particular value, all right? These little bits, each one is less than the previous one, and we also assume that the limits of those little bits goes to 0, all right? Which means when you go back and forth like this over and over again, they will stabilize to some particular value. So this is the idea of why you should believe that the series converges. So it could go to 0.5. I mean, that would depend on what precisely these numbers are, B1, B2, B3. We're not assuming that you know, for instance, B1 is a half, and then B2 is a fourth, and then B3 is an eighth. If it did that, you could be able to predict where it ends up. But these could be any numbers that get smaller every time. They don't have specific values, so you can't really tell where they're going to end up. So anyway, I'm going to say, so the the sums, the partial sums, Sn, they do stabilize to a specific value. And that means that the series converges. The series we were talking about is -1 to the n minus 1 times Bn. Converges. All right? This is why it converges. Remember, what needs to be true is these two things. So this is what you should remember for the alternating series tests. The terms have to get smaller every time. Each one has to be smaller than the previous one, and they have to go to 0 in the limit. All right? I want to just do a couple examples. This alternating series test is not so difficult to do in examples. To show that an alternating series converges, you just have to demonstrate those two things. The terms get smaller every time, and they go to 0. All right, so let's try a simple example. How about let's show that this, well, I'll just write it out. 1 minus a half plus a third minus a fourth plus a fifth minus, etc. This alternating series converges. All right. This one, there's not really all that much to say about it, but if I write it out as a series, so this is -1 to the n minus 1 times 1 over n, right? You can tell here the pattern of the terms themselves is each one is just 1 over n. And then the alternation, I put an n minus 1 here because it begins with a positive, right? So this, when I write it as a series, as a summation, it looks like this. Here's the alternation of the sign, and then this is the individual terms themselves. So here, my sequence Bn is 1 over n. Remember, the b's, just the terms themselves without the signs. All right, so this is a easily confused little point here, but the Bn doesn't include the sign. All right. But my intention is to use the alternating series tests, and so we'll show those two things. We need to show the two parts, Bn plus 1 less than or equal to Bn, and lim n goes to infinity, Bn equals 0. These are the two things that needs to be true in order for to use the alternating series test. But in this particular example, those two things are both very easy to demonstrate. Now, sometimes they can be tricky, but here, very easy. So first thing is Bn plus 1 less than or equal to Bn. What does that look like? So I'm just going to sort of plug into the formulas here. This would say Bn plus 1. So using this formula right there, Bn is 1 over n, so the right side of this inequality is just 1 over n, right? The left side is B sub n plus 1. It means you go up here, but instead of n, you use n plus 1. And so B sub n plus 1 is 1 over n plus 1. And you got to ask yourself, is that really true, this inequality? Is it true? And the answer is, yeah, it is, because the thing on the left has a bigger denominator than the thing on the right. And so the left side is smaller. So I'll just say this is true, since the left side has a bigger denominator. All right. That was the first part. We got to demonstrate that the Bn plus 1 is less than or equal to Bn, and also that lim n goes to infinity Bn equals 0. That's even easier in this example. What is lim n goes to infinity of Bn? Well, Bn is 1 over n. And what is the limit as n goes to the infinity of 1 over n? It is 0, right? The denominator there becomes 0. Sorry, the denominator becomes infinite, and so the limit of that thing is 0. All right? That's the end, basically. So these two things are true, and so then I can just say, so by the alternating series test, the sum minus 1 to the n minus 1 bn converges. That's it. So if you see an alternating series, to show it converges, you got to show those two things. The b's decrease every time, and the limit of the b's is 0. And usually those two things are going to be easy to show. In this case, they were quite easy. Any questions about that one? It says that it converges. You don't know what it converges to. And in fact, in this particular example, just because I told you before, the actual thing it converges to is the natural log of 2, which requires very strange methods to get that as the answer. So the alternating series test does not tell you what the answer is. It just tells you that it converges. All right, great. Let's just try one more example, and then we can move on to something else. I don't want to go too far since we have the test on Wednesday. We'll try one more example. How about this alternating series? 1 minus a half plus a fourth minus a eighth plus a 16th minus, I guess the next one is a minus. All right, this is another alternating series. Does it converge or not? You can kind of just look at this and say, yeah, it does. Although, you know, I want you to write out the details. What are the details? First of all, the terms themselves have to be, each one is less than the previous one. You can tell that that's happening here. Each one of these is less than the previous one if I ignore the signs. And it also needs to be true that the terms themselves are going to 0 as you go out to the right. And that also is pretty clear just by looking at them. So you should feel good about using the alternating series test here. This time, we should write a formula for the bn's, though. What is the bn, a formula for bn in this case? Those are the individual terms. Yeah, 1 over 2 to the n. That's a formula for the individual terms if we ignore the signs, right? They have pluses and minuses in them in the original series, but when you're doing the alternating series test, you only care about the terms themselves without their signs. These are the absolute values of those terms if you care. All right? Okay, so let's see if we can verify the two properties. Bn plus 1 less than or equal to Bn. Is that true or not? Well, it would say, in this example, 1 over 2 to the n plus 1 less than or equal to 1 over 2 to the n. And again, this is true because the thing on the left has a bigger denominator. So this is true. I'll say LHS, that means left-hand side. Also my abbreviation for my high school. LHS has bigger denominator, right? And then the other one is that the limit as of Bn is 0. So we also need to demonstrate lim n goes to infinity Bn. What is it? Well, that would be lim n goes to infinity of 1 over 2 to the n. And this is 0 because the denominators are becoming infinite. And the numerator is not. There you go. And so I'll just say a little concluding remarks. So by the alternating convergence test, or alternating, what did I call this? The alternating series test. I just said alternating convergence test, but by the alternating series test, this thing converges. I'll just say the series converges. Right, there you go. By the way, this one is actually not so difficult to actually compute the value of the series. This one here is this one is actually a geometric series. This is a little review for the test. Can we compute it? In this case, you can. It was, I'll write it again, 1 minus a half plus a fourth minus an eighth plus a 16 minus, etc. This one, actually, when you look at it, you should recognize that it is a geometric series. That is, each term is the same multiple of the previous term, right? The ratio of one term to the previous is always the same. In this case, this is geometric with, I hope you remember this business, the A and the R, right? The A and the R. The R is the ratio of each term divided by the previous one. So if I just take the first two terms, you do the second one divided by the previous one, which would be -1/2 divided by 1. That's how you find the R. It's the ratio of the each term divided by the previous one, which, of course, that's just -1/2. And the A, anyone remember what the A is? There isn't really a specific n value here. The n increases forever. Any folks at home remember this? The A is important because the sum is A over 1 minus R. This is like the formula for what it actually adds up to was A over 1 minus R. Anyone remember how you get the A? Somebody shout it out if you remember. I hope you remember by Friday. The A is just the first term of the series. It's not hard to find. You just have to remember how to do it. A is the first term, and the R is what's called the common ratio. So the A is 1 in this example. It's just the first number. That's where the A comes from. All right, and then I said the sum, I put an E at the end. The sum, I meant the sum. The sum is A over 1 minus R. Remember, it only converges if the R in absolute value is less than 1, but it is, so it does converge in this case. So absolute value R is less than 1, so it converges. And the sum is A over 1 minus R, which is 1 over 1 minus -1/2, which is 1 over 3/2, which is 2/3. So this one actually adds up to 2/3. So actually, you don't even need the alternating series test for this one, because here, I mean, I just explained another reason why you should believe that it converges, which has nothing to do with the alternation. It's just because it's a geometric series. But you can also argue this with the alternating series test. All right. This is really all I wanted to say about the alternating series test. The particular examples that we're going to do of this are going to be pretty simple in nature. Actually, if they're much more complicated, then this step right here can become quite difficult to do, because it is working with these inequalities. If the sequence terms are really weird, this step right here can be quite difficult. So for this one, really the examples we're going to do are mostly going to be pretty straightforward. Got any thoughts about that? All right, I got just a little bit to say about the next section. I don't think I'm going to go till 10:45, if that's all right. I don't know. We'll see. I don't mean to get your hopes up. I shouldn't say things like that. We'll see what happens. The next section is called Absolute Convergence. There's another type of convergence which is somehow like even better than ordinary convergence, and it's called absolute convergence. You know, we've been talking all along about whether or not something converges. Some series which converge, in fact, even better, they absolutely converge. This is the terminology. So there's another version of convergence, which is a little fancier. It's actually not much fancier at all. It's not very complicated, but it's stronger than just ordinary converging. So here's an example of one I would like to consider. This alternating series where you add and subtract the 1 over n's. Oops. So plus a third minus a fourth plus a fifth minus a sixth plus, etc. All right. This has a name, actually. This is called the alternating harmonic series. The harmonic series, remember, is the sum of 1 over n. This is like that, but you alternate. And this one converges, right? We just did that example. Using the alternating series test, we showed that it converges. And in fact, I told you that the value of that is natural log of 2, but it doesn't matter. It converges, all right? But here's what I want you to consider. If we took the absolute value every time, if we like ignore the signs and just make them all plus, this one diverges, right? Making them all plus every time, this one diverges. And why is that? Well, this is called the harmonic series. It diverges. This is a p series with p equals 1. And according to your rules about p's, this one diverges. All right? And so what you see here is the first one converges, but if you put absolute values around everything, which is to say make all the signs positive, it then no longer converges. All right? So it converges, but if we do absolute values everywhere, then it no longer converges. Right? In fact, this second one, when we have absolute values, this actually sort of adds up to infinity, right? The sum there goes to infinity. Whereas the first one, you add up a bunch of stuff, but it doesn't go to infinity. It goes to the natural log of 2, all right? The fact is, sometimes if you take absolute values everywhere, it can make the answer bigger because it used to have negative parts, which are now becoming positive. And sometimes it can make it so much bigger that it diverges, okay? So the original series converges, but if we do absolute values, then it no longer converges. So the terminology here is we say that, this original thing that I started with is convergent, but not absolutely convergent. So the word absolutely refers to like absolute value. So it is convergent, but not absolutely convergent. So absolutely convergent refers to when you take absolute values of the whole thing, does it still converge? All right, that's what the word absolutely means. So I'm just gonna write that as a definition here. We say some series, sum a to the n, is absolutely convergent when the sum absolute value a to the n converges. Right? If the sum of the absolute values converges, then it's called absolutely convergent. All right? And if that's not true, like in the example above, we had one where the series converges, but when you take the absolute values, it diverges. That has a name also. So if the sum an converges, but the sum absolute value an diverges, it's called, this one converges but not absolutely, it's called conditionally convergent. Conditionally convergent. Conditionally, it means, yes, it does converge, but it only converges because of the signs, right? Because if you make them all plus, then it diverges. So conditionally means like it only converges under the condition that you keep the signs the way they are. If you were to change the signs, it would diverge. That's why the word conditionally is meant to connote, is meant to indicate. It converges, but only because of the signs. That's called conditionally convergent. So that, that example that I said at the beginning, this is conditionally convergent. That means it converges, but not absolutely convergent. Conditionally convergent. All right. And there is a theorem about absolute convergence, which you can actually use as yet another convergence test. And the theorem says that this is something that I said before, but we didn't actually explain why. If something is absolutely convergent, then automatically it is convergent. So absolute convergence is somehow like bigger and better than the ordinary convergence. So the theorem just says if the sum an is absolutely convergent, then the sum an is convergent. Right? So absolutely convergent is somehow like better or more extreme than ordinary convergence, because if something is absolutely convergent, then automatically the original series converges. All right? I want to give us some idea of why this is true also. This one actually we can give more or less a real proof. This is not going to be super technical, but so it says if it is absolutely convergent, then it is ordinary convergent. What we have to do is, I'm going to say something like, we begin by assuming that the sum an is absolutely convergent, right? So that means the sum absolute value an converges. And what I want to demonstrate is, we want to show that the sum an converges, right? That's the conclusion of the theorem, right? The theorem says if an is absolutely convergent, then the sum an is convergent. Okay, so we assume that the sum is absolutely convergent, that is, the absolute values converge, and what we want to show is that the sum itself converges. All right. How do we do that? It's a very simple but sort of cute trick here. The trick is, check it out. What do I get when I do an plus absolute value of an? This is just a general fact about numbers in general. If you add some number plus its own absolute value, maybe I'll just do this on the side here. For any number, x plus absolute value of x, it either equals 0 or 2x. Yeah, why is that?
Because you're adding the same value twice, or you're adding the value.
Yeah, right. So it's basically like if x is negative, then what you see here is a negative plus the positive version of that same number, then it'll add up to 0. If x is positive, then what you see here is just x plus itself again, which will add up to 2x. So this is either 0 or 2x, right? That's it. And in fact, when it is 2x, it's that's also the same as 2 absolute value x, because the 2x part is what happens when x is positive. Yeah, sure. I'm going to go back here, but what I'm going to say, x plus absolute value x is either 0 or 2x. So this is 0 or 2 times absolute value an, right? And in particular, what that means is, you can write it, now ordinarily, this is a sort of a weird step, but it's certainly true. This is less than or equal to 0 and less than or equal to 2 absolute value an. Now, in fact, that thing is never any number in between, but what I wrote is still true. It is either equal to 0 or it's equal to 2 absolute value an. It actually can never be anything in between. But anyway, so that means an plus absolute value an is positive, because it's bigger than 0, or equal to 0, but I don't care about that. And it's less than or equal to 2 absolute value an. All right? And what that means is I'm going to use the comparison test. Remember the comparison test you use when the terms are all positive? Which these are. And when they're less than something else. All right? So an plus absolute value an is positive, and it is less than or equal to 2 absolute value an. So we can do the comparison test. with an plus absolute value an being less than or equal to 2 absolute value an. And when I sum these, the one on the right converges. That's because I said at the very beginning, we assume that the sum of absolute value an converges. So when I do the sum of this, it does converge. It has a 2 on it, but that doesn't affect the convergence or not. Since this one converges, it means the smaller one also converges. So I'm going to say since the sum absolute value an converges, by the comparison test, the smaller one also converges. Also, the sum an plus absolute value an converges. All right. But that means since I'm adding those things together and it converges, that means I can split it up since I already know the absolute value of an's converges. So that means the sum an plus the sum absolute value an converges. You got to be a little careful when you split up a series like this, but this is legal because we already have assumed that that this part does converge. So we can split that off into its own thing. And that means that the first part also converges. So the sum an converges. And this is what we wanted to demonstrate. All right. So if you know the sort of short version of all this is if you know that absolute value converges, then you can compare using the comparison test, comparing the original series to its absolute value. And everything works out great. All right. This is the end of that little proof. Anyway, I want to do just one example, and then that'll be all I have for today. So we can use this to show certain weird series converge. Remember, the theorem said if it is absolutely convergent, then it converges, right? So that means if you want to show that something converges, it is often successful to instead show that it absolutely converges, because absolute convergence means automatically that it does converge in the ordinary sense. All right, that was the theorem. So let's try it on this example here. How about the sum sine of n over n squared? And my goal is I want to demonstrate that this converges. All right. My idea is I would like to compare using the comparison test with 1 over n squared, right? Because the sign up top there, like the sine of n is never going to be super big. It's always between 0 and 1, right? Or it's between -1 and 1. And so I would like to use the comparison test, comparing this with 1 over n squared. The problem is the comparison test only works when you have positive terms, all positive. And this is not all positive. So the problem is, but absolute value, sorry, not absolute value, but sine n is, I will say, often negative, right? So you can't use the comparison test directly. But if only we had absolute values in there, the comparison test would be legal. And so the theorem, though, says if it absolutely converges, then it converges. So my strategy is we will show that it is absolutely convergent. This allows you to insert absolute value signs, which in this example actually makes it easier. So we'll show that it is absolutely convergent, which, according to the theorem there, means it is convergent. All right, so instead of showing that it converges, I'm going to show that it converges when you take absolute values. And that turns out to be easier in this example. So I'm going to take absolute values on the inside. Absolute value sine n over n squared, like that. Absolute value of a fraction is the same as absolute value of the top and also on the bottom. The bottom is already always positive, so this is really just the same as this, right? And from here, we really can do the comparison test of this versus 1 over n squared. I think this is just easier if you just do the standard comparison test, not with the limit comparison test. But anyway, this I'm going to compare with 1 over n squared, right? So first of all, it is true that absolute value sine n over n squared is less than or equal to 1 over n squared. That's because the numerator on the left side is is less than 1, right? It's between 0 and 1. Since the left-hand side has a smaller numerator. All right? So this is our comparison. And when you do the series, the bigger one converges. 1 over n squared converges. That's because this is a p-series with p equals 2. And the p-series converges when the p is greater than 1. So this one does converge. The bigger one converges, and so that means that the lesser one also converges. So the sum absolute value sine n over n squared converges. And so the point of all this was that that means that the original series, sine n over n squared, is absolutely convergent, because we showed that the absolute value converges. And so that means it is convergent. And that's the end. All right, so you can, if the series is too weird, you want to use the comparison test, but it's negative sometimes, you can just take absolute values everywhere and then use the comparison test. That's sort of the moral of this little trick here. And I think that's going to do it for today. That's all I had to say for now. So we will revisit this a little bit, I guess a week from today. But tomorrow, we will just talk about review for the test. All right. See you all later. Homework is due tomorrow also. All right. Bye-bye.